All right, welcome back. So I have a confession to make since I don't often use Laplace transforms in my own work. Um, Generally something that I only use when I do differential equations, but I know that that it is something that people use, okay, especially in some of the applied areas and in engineering. So I was a little wrong. I don't necessarily need s greater than 0. It's just here. I've corrected that in the notes, so when you look in the PDF, it'll be there. We often need that. That's often the case, but the Laplace transform is defined for all s so that the integral exists. Okay? That last problem was bothering me. That's one of the things that happens as you do math. You start to see things, you're like, you know what, something's wrong with my own understanding. And you see, and like, so the proper condition for this Laplace transform to exist was that s was not equal to 0, just like I had thought could work. Okay, not s greater than 0, the s not equal to 0. Okay, so I've corrected those. The next thing we're going to talk about is what's called exponential order. So, and this is actually really the whole piece. So suppose, so we say f of t is of exponential order alpha. So that's what we're defining here. If there exists t and m both bigger than 0 with the absolute value of f of t less than or equal to m e to the alpha t for t greater than or equal to t. So what does this mean really? Okay, if I look at this and I think about this in terms of a graph, okay, what this really means is that I have some t out here, okay, and I have some exponential. So this exponential is my m e to the alpha t, okay, and my function can do whatever the hell it likes before that function, before that bound. Okay, it can do whatever it wants here. But then once it goes past that t, it's not going past that thing. Maybe it's close, maybe it's away, maybe it's close again, but it's not going to go and grow farther than that. Okay? And really, I shouldn't even worry about what it's doing on the negative side. Okay? I don't care what it's doing on the negative because my Laplace transform doesn't care about negative times. Okay? It just doesn't. Okay? All right. So once we have this, we have our theorem. Okay? If f is piecewise continuous on 0 infinity and of exponential order alpha, then the Laplace transform, the Laplace transform of s equaling the integral from 0 to infinity e to the negative st f of t dt, it exists for s bigger than alpha. So that's where I sort of was getting that my s had to be bigger than 0. But there are other situations as well. So in most situations that we care about, that's what happens. But as we saw, there was a situation where it could have been different. Okay? The Laplace transform is what we call linear. And when I say it's linear, what that means is it satisfies these two conditions. One, L of F1 plus F2 of S equals L of F1 of S plus L of F2. Oh, let me move these a little bit to the left. Move that as well. And then the second thing is L of alpha of F1 of F is alpha L of F. Okay? One thing that's a little bit funny is that most of your regular lines that you think of are not what we call linear. Okay? And that's because of this thing, this condition. This condition means that the lines have linear here in this sense means it's not just a line, but it's a line that goes through the origin. Okay? All right, so let's go ahead, let's take some Laplace transforms. Okay, we're going to take the Laplace transform of five minus e to the 2t plus 6t squared of s. Okay, so now, because it's linear, this is going to be the Laplace transform of 5 minus the Laplace transform of e to the 2t plus 6, the Laplace transform of t squared. I should have put s's on here. Move this down. Okay, now the Laplace transform of 5, also because it's linear, that's going to be 5 Laplace transform of 1. Okay, minus, can't do anything else with this one, plus, yeah, we can't really do anything else with this one either, because I already pulled the 6 out. Okay, well, we did the Laplace transform of 1. The Laplace transform of 1, we wrote that, that's 1 over s. Okay, look back at that first page. Laplace transform of 1 was 1 over s. Oh, wait, we did Laplace transform of 1 over of e to the at as well. We need that one. That was 1 over s minus a. So the Laplace transform of e to the 2t is, by the way, here we need s bigger than 0. Here it's 1 over s minus 2, and we need s bigger than 2. Okay, plus, 6 times the Laplace transform of t squared. That means I'm going to have to do an integration by parts in t squared and e to the at. Well, let me go ahead and do that with Sage. So I'm going to share my screen on Sage. Oh, give me just a second. Okay, I am now the host. Let me just change a couple things here. I can allow share screen. I can share my screen. Let's go to there. Okay, had to learn something. There we go. There we go. Laplace transform. Okay. So here I'm setting up for us to take the Laplace transform. Now I'm setting it up pretty vaguely, in the sense that I can pretty much do the Laplace transform of any function with this little bit of code. Okay. Now I have commented out the assumption that s is bigger than 0 on purpose. I want you to see what happens when I do it without that assumption. A whole bunch of error codes. Okay. Why? Because this integral, you can't do it when s is without that assumption. So let's make my assumption and see what happens. Okay. I get 2 over s cubed. Let me just check and make sure that's what I got last time I did this. Somehow it feels like it wasn't. Nope, it was. Okay, so that's 2 over s cubed. I'm going to real quick go back to the other page with that knowledge. Let me stop this share real quick. So we found that the Laplace transform of t squared was 2 over s cubed. Should have written that down somewhere. With s bigger than 0. So we need our overall restriction is that we need s to be bigger than 2. Right? If s is bigger than 2, then all of these exist. So I'm just going to get rid of these two and say s bigger than 2 is my overall assumption here. Okay. All right, we're going to come back, do one more with the computer, and that'll be it.